Hi, good morning, good afternoon, good evening from wherever you are tuning in. My name is Hao Min Tan. Welcome to PTV Drive In, a place where we talk about all the newest development on traffic and automotive virtual testing. Today, our presenter is Shyam Sundar Rampalli. Shyam is a research associate at Nanyang Technological University here in Singapore. He is currently involved in research activities at the Center of Excellence for Testing and Research of Autonomous Vehicles. So in short, maybe you have heard of it, it's called CETRAN. And prior to his work at NTU, he acquired academic knowledge with his master's degree from Technical University of Munich, specializing in transport engineering. His main research interests are autonomous driving, traffic simulation, and driving behavior modeling. So without further ado, I pass you on to Shyam today for his presentation on virtual evaluation of AV's introduction to public transport. Enjoy.
Thank you, Hamin, for the nice introduction. Hello, everyone. Good afternoon. Today's topic for presentation will be virtual evaluation of AV's introduction to public transport. So the idea is to evaluate AVs virtually in the case when they are deployed for public transport. So the contents of today's presentation will be a brief overview, followed by the research project that I was working on, and then I would talk about the behavior modeling in Vissim, followed by the challenges or the requirements for behavior modeling for AVs in Vissim. And then I would talk about the AV behavior with Apollo, how it can be modeled, and what are the changes that we have done, and what are the changes that we have inculcated in Vissim. And then I would talk about the proposed design, the details of which I would talk about it later, and then followed by results. And then I would give you a future scope of how this research can be extended. So first things first, introduction, a broad view. Microscopic traffic simulation has a simplistic mathematical model for different vehicle groups such as car, motorbike, and pedestrian. Along with these models for different vehicle groups, it is possible to customize the models for individual vehicles in the simulation. While such a modeling is observed in groups, it's also possible individually. AV simulation, on the other hand, follows complex, detail-rich, modular mathematical models. It uses a modular approach wherein there are certain modules that are handled differently and are modeled individually, and they work together as a system. Perception, as you can see here, refers to the human eye and the human brain. Prediction and planning refers to the decision-making part of the brain, which is a supposed replacement. And control refers to the actuation. It could be a steering wheel, or it could be a throttle or brake, etc. HD map and localization refer to the location of AV, either virtually or physically on the roads. So now we can see that the microscopic traffic simulation and AV simulation model vehicles in a different way. Both can learn a few things from each other. Traffic simulation, on one hand, can assist AV simulation in scenario generation and realistic traffic simulation. Predominantly, AV simulation relies on scenario generation based on certain mathematical equations or from experience. Traffic simulation, on the other hand, can assist AV simulation in detecting few scenarios which are not traditionally detected from experience or from certain mathematical models. As I've mentioned earlier, traffic simulation uses simplistic mathematical models, but The AV behavior, implementation of AV behavior in traffic simulation can be a challenge. And this, at this point, it's fair to say that traffic simulation can learn from AV simulation about the AV behavior. So certain models, either offline or online, depends on how you implement it, can enrich traffic simulation when AV behavior as a lesson learned from AV simulation is implemented. The next thing that I'm going to talk about is a research project that I was working on. So the first part of my research was modeling highly accurate perception and autonomous behavior of the vehicle by using multiple third-party software, which are predominantly capable for AV simulation. So the idea was to replicate realistic AV behavior. Along with the AV behavior, the idea was to replicate realistic traffic behavior, because most our predominant AV simulation tools do not have realistic traffic. And it can be challenging, depends on which tool you are using. Another part was to also concentrate on the environment models that you use in your virtual testing tools. So since our area of interest was in Singapore, we used Singapore environment models, which aid in evaluating sensor physics of the vehicle. The second part of our project was to redesign parking areas and MRT stations. So MRT stations refer to the metro stations, to maximize AV loading or unloading and commuter throughput. So the idea was, let's say in future, if AVs are deployed for public transport, and we want to see how can we integrate the AVs into the existing public transport. So the idea was to propose various bus stop designs. So how do we do that? Is to actually modify the existing bus stops. So the design would include a dedicated stopping point for AVs. So we compared certain advantages and disadvantages of these designs. Along with that, we implemented these designs in a microscopic traffic simulation model to evaluate, maybe not just to compare, which was the initial idea. The next idea was to evaluate how these designs can benefit if AV is realistic enough. So this part of the project is where I try to implement, I try to understand AV behavior and and also the traffic behavior. So this is where I decided to use Vissim. And yes, I'm going to talk about how the behavior is modeled in Vissim before I talk about the AV behavior with Apollo. So behavior modeling in Vissim predominantly uses two models. One would be the car following model, and the other model is the lane change model, which I thought were more relevant for our use case. So the car following behavior is modeled with two renowned models. So the first one would be the Wiedemann 74 model, which is for urban traffic. The second one is the Wiedemann 99 model for highway traffic. The Wiedemann 99 model has more parameters, and it is easy to customize and calibrate your own model, if any. If you have your own model, it's realistic to use Wiedemann 99 model. Even though it's more relevant for highway traffic, it's possible to include your behavior and use it for your own urban use cases. And the other behavior is the lane change behavior, which predominantly relies on maximum deceleration of your own, the self vehicle or ego, and the trailing vehicle. Along with the maximum deceleration, safe deceleration is another value which is observed to be quite sensitive when modeling lane change behavior for the ego and the trailing as well. Now that it's clear to understand the vehicle behavior in Vissim, it's also important to understand how AV behavior can be adjusted to this lane change and car following model in Vissim. For that, we need to understand certain parameters such as longitudinal range of visibility, lateral range of visibility, safe braking distance, safe lane change distance, driver attention, which can be a probability number, safe overtaking distance, so on and so forth. So when all these values are translated for an AV, it depends on what sensor setup AV is using. So AV has different sensors that are installed, and each sensor comes with a range. And it's also up to the AV to detect an object, a static or a dynamic object, and react according to that. So all these parameters, when translated to AV, depend on the range of the sensor setup, what's the longitudinal, rear, and the lateral, and also the efficiency of AD stack. How long would it take for an object to detect and translate, and then actually react? So it depends on the AD stack. However, for modeling purposes, we can actually observe the behavior of AV and then calibrate the existing models in Vissim, and that's what we have done, which is the which is AV behavior with Apollo. So how did we do it? Is we used the Wiedemann 99 model, which I've mentioned earlier because it's easy to modify. And we use, so to the right, you can see a table which has certain parameter values: standstill distance, headway time, following variation, threshold for entering, following, etc. And the default values are the values provided in Vissim, in the software by default. And we ran few set of experiments to actually see if these values are followed by Apollo AV, and certain values such as standstill distance, headway time, and following variation were observed to be slightly different, while certain values such as negative following threshold, positive following threshold, and speed dependency of oscillation were not found to be very sensitive. At least when we changed the values, there was not a significant difference in the Apollo AV, so we thought it's not, so we did not test further, and then certain other values such as standstill acceleration was found to be higher. At least this was the value that we were using for our AV. And the lane change behavior, 4 parameters of the lane change behavior in Vissim were found to be more relevant for us and also more sensitive to the lane change behavior. So we changed the maximum deceleration to be -4 and accepted deceleration to -2. And the advanced merging, at least was, we did not apply this for our case, so we did not use it. And then we increased the headway for safety purposes. How did we do it? The workflow was, as we have calibrated AV behavior with Apollo, we have designed a virtual environment within Vissim using some open source resources such as OpenStreetMaps, and then we validated it using Google Maps and also with on-field visits. What was our area of interest? I will tell about it in further slides. So how did we achieve this workflow? So we used the Python COM model of Vissim, which really saved us a lot of time, where we were automating our simulation executions, and Vissim would real-time send the road network, traffic signal data, and vehicle values, etc. And then the COM interface would communicate with Vissim with the simulation parameters, random seed, and the other values. So this is how we implemented the workflow. Now, more interesting thing is how do we use this achieved workflow? So that brings us to the proposed designs and results, which is the main essence of our research. So we had an area of interest in Ang Mo Kio in Singapore, and as I mentioned earlier, the idea was to propose bus bay designs in Singapore. So we had a chosen location where we intended to do that with a virtual analysis with Vissim. And for your reference, the top one is the three-dimensional view, and the bottom one is the two-dimensional view of the location. So what are the proposed infrastructure designs? We proposed 3 bus bay designs. The first is the shared AV bay. The second one is the elongated bus bay. And the third is the exclusive AV bay. How would each of the design look like? The first design is the shared AV bay. What's the meaning of this? Shared AV bay, shared bus bay is actually an extension of the existing bus bay in Singapore. So if we model that in Vissim, it would look similar to this, where you have an AV bay, and behind that you have stopping points for AVs. So in Vissim, we model our AV as a car, since Vissim does not consider certain parameters such as weight and dynamics. So we used car as our AV, our proposed AV, and we modified the loading bay into a bus stop. So on the bottom, you can see there's a loading bay. So we modified that into a bus stop and allocated a designated stopping point for AV. Here is the simulation render of the shared AV bay or shared bus bay. You can see this stopping point for AV where people would get down and then get in. This is how we have, and the AV, the car in yellow color, includes the calibrated Apollo parameters. Another design is an elongated bus bay. So in Singapore, when at the bus stops where there is higher traffic, there would be a double bus bay. Our idea was to extend the existing double bus bay and include a dedicated stopping point for AVs. So as you can see, the AV has yellow color and it has a dedicated stopping point in the middle of both the bus stopping points. That's one idea. Another idea is to have an exclusive AV bay. How does that work? The idea was to have a stopping point behind, physically located behind the AV bay. The bus bay. And this is how it would look like. So there would be a bus, and then there would be an AV stopping point physically located behind. Some simulation render can help you visualize what I am trying to say. So there would be a bus stopping point, and behind that would be a AV stopping point. So the next step would be the results. How did we try to evaluate? The measures of effectiveness that we used for this research was travel time and queue length. We observed that for different designs, so we calculated the travel time for different designs and also for AV and car and other vehicles separately. We realized that the travel time for AVs is different for different designs. AVs take the longest time for shared AV bus bay, and for the exclusive AV bay that I've shared just now has the shortest travel time, which also translated in queue length, where the queue length was the minimum for exclusive bus bay, while a bit counterintuitively, the elongated busway had the highest queue length. We observed this because there was a queue formed up behind the bus stop when there was high traffic. So that's the trade-off. As we try to reduce uh, the travel time for AV with different designs, we observed that the travel time for car and all the other vehicles, as you can see from the graph on the left, increased. So that is one trade-off that we observed, and we realized, okay, so we wanted to study this further. So that's for the future scope of our research. So I will talk about that. So the idea is, since we observed a trade-off where when we try to prioritize AV and reduce its travel time, we realized that the other traffic had a higher travel time. So in future, we would like to test this in other parts of Singapore. And once we have this consistent observation, then we will try to see it in the other parts of the world. We are also interested in impact of AV behavior on crowded pedestrian scenarios, and also translate this this use case to first mile and last mile applications in transport. So with that, I would like to thank you all for your time to attend today's presentation, and I would look forward for any comments, questions, or clarifications.
Thanks, Shyam, for the great presentation. Super insightful. Right now, I will just go through and before we go to question and answers, I will just share a little bit with you all for the next event in August. It will be about humanizing CAV development, and the presentation will be from Dr. Thomas Benz, our Solution Director, Automotive in PTV Group, and also Banu Kala from the Americas Automotive Lead in PTV Group as well. So if you want to know more about this event, please go to the Drive-In page and you can also register from there. So for the next step, we will go into the questions and feel free even now to input any questions you have. And since Shyam is also here with us today, it will be great for him to answer live. And if there are any questions later on, feel free to also reach out to us and we will come back to you as well. So let me start with a first question. So have you tried to inject nanoscopic traffic from other simulation packages in order to enrich the variety of participants' behavior?
We have tried it with Sumo as well. Uh, however, we realized that there are certain, I mean, the driver behavior models are different compared to Vissim, and we were not sure about how it can be efficiently calibrated. So we restricted ourselves to just Vissim.
Okay. And oh, yeah, sorry.
Yeah, please
And
continue.
yeah, so for the next question, and also I think maybe following up from the previous one, you also mentioned, I think when we chatted, that you'll be publishing a paper more of this information from the presentation today as well, right? So
Yeah,
I'm very much looking forward to that. Yeah.
yeah,
Okay, so
okay,
moving
yeah.
on. Yeah.
Forgot to mention about that. We already published a conference paper on the designs that I presented earlier, uh, and we are also looking forward to extend this research in terms of what I've mentioned earlier about the future scope, and we are also working on a journal paper. Yes.
Perfect. Really looking
Yeah.
forward to it. Okay, for the next question, with the exclusive bay for AVs, it looks like you would create a new conflict area where bus passengers have to cross the path of the AV. This may lead to increased risk and waiting times. Did you take these effects into account?
Yes. we also consider that into account for sure. However, we this kind of a design makes sense. We try to avoid more pedestrian and AV conflicts. I understand this is more challenging to implement, but this was an idea to understand whether uh, physically separating AVs from the bus stop is it more interesting or not. That was the main idea. Yeah, of course, it's important to consider pedestrians. We had this case, but we did not simulate this because we really not sure what's the strength of the AV models, what are the strength of the existing AV models and how they would react to pedestrians. So this is also an interesting idea, but we uh, did not simulate it. But that was one of the thought when we came up with this design. Yes.
Okay, great. And moving on to the next question, did you check why the travel time for cars increase with AVs being present?
That's because of we observed that because the car's travel time increased as there was some queuing, and then while we were simulating, there was some issues where when the traffic was pretty high, we observed that the AV would take some time to actually enter the bay, enter the bus bay, and by the time it would leave, there would be a queue building up, and there would be a heap of cars behind it. So that was our observation.
Mhm. Okay, for the next question, so how is the perception simulated? Did you manage to simulate a sensor from a render to recreate a scenario, or from the data model from Vissim, you got the sort of like vehicle positions, the angles and the lengths, etc.?
Okay, so for the perception, we actually used the modular testing component of Apollo, which assumes a perfect perception. So we did not test any sensors in this because that was not the idea. Yeah.
Mhm. Okay. So following up from the previous question, I think about the travel time for the other cars, there's a
Mhm.
follow-up saying, why does travel time for cars depend on the bus stop design?
Because for different designs, it was more about how the AV behaved when it tried to enter and leave the bus stop.
Mhm.
So for different designs, for example, the shared AV bay, the queue was basically when the AV took time to enter the bus bay and leave the bus bay. That was one reason why there was queue formed. For the elongated bus bay, where we mentioned that there were two buses, uh, so there was a situation where AV would try to enter the bus bay, and then there would be a bus waiting for it, and behind the bus there would be a queue building up. So it's mostly about how AV behaved when it tries to enter and exit. So we wanted to avoid the interaction between the buses and cars at the bus stop, and that was the reason why we had an exclusive AV bay as one of the designs.
Yeah, great. Yeah, so there's the next question, which says, a great presentation, Shyam. What scripts was required? Was it to test many different parameter values?
Yes, many different random seeds and many uh, and also the traffic loading time. So we had to wait for like few minutes for the simulation to start, and then after that would be a realistic traffic, because in the initial stages of the simulation, the road would basically be, I mean, the traffic would still be loading and it's not realistic. So that's where simulation assisted us. And also to test with Apollo, where we modified certain parameters of the car following model, and that's where Python also helps. Yes.
Okay.
Yeah.
Right, that looks like all the questions today. Maybe from my side, maybe it's obvious, but who came up with the idea of Apollo?
Sorry.
Who came up with the idea of naming it Apollo?
Okay. Name. I mean, Apollo is a driving uh, simulation software, like an AV AI engine for the AV. So it's like a replacement for the human driver. So it's the brain
Mm-hmm.
of the human driver. So there is an existing software. It's Baidu Apollo. I'm not
Okay.
sure. Yeah. So we used that software to actually calibrate the AV behavior in Vissim. Yeah.
Okay. Great. Great. Yeah, that's all for today. Thanks for the great presentation, Sham, and then for also answering the questions.
All right.
And yeah, looking forward to your publication. And thanks all for tuning in. And we will see you at the next event in August. Have a good day.
Thank you.